Okay. So you know, I mean, we learned we also learned if some value is eigenvalue, then we learn how to find the eigenvectors. Yes, sir. Right? Using the definition of null space, right? So that will be today's topic. Instead of giving you just eigenvalue from the beginning, what if you want to find the eigenvalue from the beginning, like by yourself? Okay, so technical difficulty. So let's say I give you yes. So let's say the lambda eigenvalue. This lambda is eigenvalue of A. Okay. I want to ask, hey, if you have 2 times A, and can we say 2 times lambda is also eigenvalue? I'm trying to see if we already know that lambda is eigenvalue of some matrix A. I want to ask, hey, if we multiply the matrix by 2, can we have a reasonable guess for the eigenvalue? Any idea, right? This can be true or false.
I want to say true.
Yes, what?
Because we know from last class that I'm going to work this terribly, but if I were to think of graphing an eigenvalue as sort of like a scalar, so anything that falls in that stands for the eigenvalue.
Yes, yes. Yes. So what is definition of the eigenvalue of 2A? One second. If I multiply 2, both sides, add to this, and then I just rewrite this. Yes. Now what does this tell us? What's the definition of the eigenvalue?
It's the scaling of the eigenvalue.
The definition of eigenvalue is so it's this ax equals to lambda x. Okay, so if we have if this is true, then lambda is eigenvalue of matrix A, right? So I can just say, hey, if I have matrix that is 2 times A, and I can also say 2 times lambda is also eigenvalue of 2 times A. It's simple. That's simple. So is this true?
Yes.
So let's say instead of 2, let's say I use 10. 10 times lambda is an eigenvalue of 10 times A. Is it also true?
Yes.
So now instead of giving you eigenvalue from the beginning, I ask you to find eigenvalue of this given matrix. And I want to use the definition we learned yesterday. Any idea? What is the definition of eigenvalue? Ax equals to lambda x. Right? I want to find lambda, right? I want to factor out x. What did we learn yesterday?
Well, lambda times a or minus lambda.
Like this. Right? Okay, so back to the chapter when we learn invertible matrix. In order to have eigenvalue, what is the condition that we had yesterday?
The non-trivial.
Yes, non-trivial solution. Great. Always impressive. So, I want to have non-trivial solution. What is the way to solve this? A creative way to solve this. We already know that this should be creative.
Just multiply the x to the matrix by.
Pardon me? You say it first.
Ax equals 0.
Ax equals to 0.
I put 0 at the end and it's reduced.
Okay, yeah, that's good. That's what we done. What we did yesterday. Dylan, what were we going to say?
Would you multiply the identity matrix by lambda to then perform the A minus the lambda identity matrix to set up a system of equations to solve the variable?
So you're trying to cancel this?
Not cancel, you get like 2 minus lambda, 3, then 3, then 6 minus lambda. You just kind of set up like a function.
Oh, okay. Well, I think I never thought of that. But anyway, let's try to use some simpler way to solve this using the fact that we learned a few weeks ago. Okay. If this thing is invertible, then what does it say? If this thing is invertible, what can we do?
Convert it.
Yeah, invert. Yes, invert it. Once you invert it, what? Invertible means we can find the inverse matrix, right? So invert means I want to multiply both sides by inverse of this and cancel this. And since this is 0, 0 times some whatever is still 0. So what we have is just x equals to 0. Make sense? So if I, okay, as Mason said, okay, invert this. Okay, so I invert it, and then I multiply both sides by inverse of this. Then what I get is essentially x is equal to 0. Then trivial solution. Right? So that means, so if I go backward, if this thing is invertible, a minus lambda I is invertible, then I'm going to have trivial solution for sure. So that means I shouldn't have invertible matrix. Okay, so this is one of the questions from the exam 1 true false question. A is invertible if and only if determinant is 0 or not 0? Not 0. Okay. So in this case, I want to have non-invertible matrix. That means the determinant that I should get is what? Yes. So I want to compute. A minus lambda I, a determinant of this thing, should be 0. And I want to find the lambda that makes this thing true. That makes sense? Do you guys understand the logic? So I'll try that, guys. Quite simple question. Is there anyone who wanna work this problem? What is determinant of 2 by 2 matrix? If we have A, B, C, D, the determinant of this thing is what? No, I'm not asking the inverse of this. I'm trying to compute only determinant. The cross multiply minus cross. AD minus BC. AD minus BC. Okay, you wanna solve this? I got started. Oh yeah, go ahead on the board. You good? Now how you doing? Okay. Yes.
Determinant gonna be in terms of lambda?
Yes. And then we want to solve for lambda. What value did you get? It's like we're gonna have two second degree equation. It's like calculus 1.
So you get one value for it?
Oh no. What, you have to set up a minus lambda minus I. What is this? We already have a. What is lambda times I? With the size of I.
There's the lambda of B.
What is lambda I to what is it? What is the invert? What is identity matrix that is size 2? 2 by 2.
1, 0, 1.
Yes, it's
0, 0, 1.
Yes, this is essentially lambda 0, 0, 0. A minus lambda I is going to be what? A minus, so I'm asking you. It's okay. Go ahead. No, it's okay. So no need to be sorry. We are here to learn. Okay, we're here to learn. What is this? I want to rewrite this. I want to write this. Yeah, 2 minus lambda. 3. 3 minus 6 minus lambda. That's it. Okay. Does that make sense? And I want to find determinant of this. The formula is AB minus BC. So essentially, let's try. Yeah, Thomas.
So if it's non-invertible, then it has an eigenvalue?
Yes, yes. And then that eigenvalue you find is, yeah, that value that we found is eigenvalue. So we solve for lambda, and you're gonna get values, right? Those are the eigenvalues for the given matrix A. Yeah. Yes, good, good, good. Yes. Minus what? No. Here, 2 minus lambda times minus 6 minus lambda, right? Minus 9. 3 times 3. So you multiply this 2, and you multiply this 2, and you subtract.
So we're just gonna throw this out?
Yeah, yeah, yeah. And you set this equal to 0. Yes, yes.
So when you solve for lambda, for when a equals 0, those are the values that a can't be?
Yeah, the eigenvalues for A. Yes, 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 yes. I'll show you. Okay, yes. Set it equal to 0. What do you get? I get the same answer. Then that's your
Plus 4 lambda minus 1. Is that what you have?
Minus 12 and 12 is 9. So it's going to be 21. So lambda square plus 4 lambda minus 21. And what is this? What was it? I forgot the name. Yeah, we have 41. Yeah. Plus 6. Yeah, got this, right? You need the formula?
Yeah.
We had that, but he erased it.
Oh, you got it? You got it? Oh, good job, good job. Thanks, good job. Thanks for your hard shot. Okay. So, then what? You set this equal to 0, and the lambda that makes this thing true is lambda is 3 times 7. Okay? Back to the original question. So we wanted to find the eigenvalue of this matrix, right? And then in order to find the eigenvalue, what do we do? We set up the determinant of A minus lambda I, and then that should be 0. So, therefore, if this thing is 0, determinant of this A minus lambda is 0, then this should be the eigenvalue of A. Okay? Makes sense? Okay, determinant. So now you feel like, okay, so now when we try to find the eigenvalue of some given matrix, determinant, computing determinant will be a really good tool. So now, let's review how to compute determinant. One of the exam problems. Try this. Anyone want to work this on the board? To review all of your friends. subtract?
Well, I was just gonna answer the
Oh,
question.
yeah, okay.
So like, I would do it from like the column of 2, 4, 0. So like,
Okay.
I pick 2, and I cross out that row,
Yeah.
cross out 3 and 1,
Yeah.
and then I take 0 times 1,
Uh-huh.
and then subtract 2 times -1.
Okay. Plus, no, actually, plus minus. Minus?
Yeah,
Four, right?
it should alternate, so it should be plus, minus, plus.
Uh-huh.
So it should be -4
Times,
times, we can
Determinant.
cross out 4's row,
this.
so it should be 3 times 1
Uh-huh.
minus 2 times 1.
Okay, good. So we keep doing this. Okay,
Yeah.
Good job. Okay. Actually, oh yeah. Kind of expected how the author would solve this. Yes.
Could you row reduce R2 using R1 first to give you 2, 0, 0?
Okay, you try this. Yeah. I think you can get the answer. Yeah. See if you get the answer. So this is one of the exam problem, right? So if the given matrix is so confusing or so complicated, you can do some raw operation to reduce the numbers, right? And then you can make it a little bit more simpler, and then you still can calculate the determinant, and still the determinant of row reduced matrix will be the same as determinant of the original matrix.
Give this 2 times determinant.
Great. So that answer, great job. Do you guys understand how it is? Understand? Okay, so get over this. And still the same answer. I mean, still the same determinant. Also, you get 0. Using Christian's way or Chris' way, same. It'll get you to the same answer. So yes.
Wouldn't it be easier to since to just take row 2 or take one of the rows and zero them out since they are first, or I'm just curious.
Yeah. So he zeroed this out. I mean, so what Chris did is I don't want to see this for.
Oh, I meant the -6, -3, and then 2 and 1. Because you.
Yeah.
Oh, you
You
could.
can use yes. You can use. Yes. Great job. So you want to row reduce one more time, right?
Yeah, just to make it even easier.
Yes. Then you're gonna have all zeros for this one. Right?
Yeah.
Okay. Yeah. That also makes sense. Yes. And that's why you still have 0. I mean, if you still keep doing this, if you keep doing the row reduction, then you're gonna have 0. I mean, all zeros, because so determinant is 0 means you're gonna have all zeros after you do row reduction, meaning you're gonna have one step back. What do you mean? What is the meaning of determinant? I mean, what is the meaning of having determinant 0? The column space or row space is going to be dependent, right? So after you keep doing row reduce, you're gonna end up having all 0 rows or all 0 columns. That's the result you're gonna get for sure. But anyway, yes. And the reason you get the 0 is because the column space or row space is determinant. That's why you're going to have all 0 rows or all 0 columns if you keep row reducing. Make sense? Well, this. Try to complete this, and then let's try to use these numbers to find eigenvalues. So this chapter of this, I mean the name of the title of this chapter is eigen. This chapter 5 is eigenvalues and eigenvectors, and then everything we learned so far are going to be tools to find eigenvalue or eigenvector. what I tested you, exam 1, right? Did I test this? Forgot.
Yeah.
Oh, really? Okay. Then you know this. Oh, I think I tested this. Okay. Okay, what about this? Is this something new? Okay. If matrix is triangular matrix, then what is it? Determinant of A is the product of entries on main diagonal. Okay. Even before we assume something is triangular, what is the definition of triangular matrix? We learned it yesterday.
The pivot columns are.
Oh, zeros for below the main diagonal.
Yes, we don't need pivot because triangular matrix is like triangular matrix is just the shape of matrix. So we don't need any row reduction. For example, like this. Even before we row reducing, even before we do anything related to this matrix, the given matrix is like triangular. You can separate this matrix into two different triangles. One, non-zero entries. The other one, all zero entries. So this is called triangle. You can also say something like, instead of having zeros here, you can just have also non-zero numbers here, also zeros here. That is also triangle. Okay. Anyway, so. Determinant of the triangle matrix is simply the product of entries on the main diagonal. The main diagonal line is okay, what is definition of diagonal? What is definition of diagonal? This can be diagonal, right? Yes. Main diagonal means is the longest one. Longest one, main diagonal. So if I ask you, hey, find the determinant of A. So yes, you multiply this 4. It's 4 numbers. That's it. Okay. Now, this is what we learned. Chris, can you read it?
A row replacement operation on A does not change the determinant. A row interchange changes the sign of the determinant. A row scaling also scales the determinant by the same scalar factor.
Okay, so what Chris did here is just only a row. Okay, row replacement. Oh, wait. What is that? Row replacement. Oh, yeah, you did this. Because he changed the second row using row 2 minus 2 times row 1. And you replace second row using this. That's why you didn't change the determinant. Okay. If I ask this kind of question, I'll give you this. I'm not going to force you to memorize this. If I have things that I want you to memorize, I'll tell you before the exam. Okay, so now we are learning new fact. Well, can you read this?
The invertible matrix theory continued. Let A be an n times n matrix. Then A is invertible if and only if the number series is not an eigenvalue of A.
Okay. So A is invertible. We got a square matrix. Same size of rows and columns. And if A is invertible, then 0 is not eigenvalue of A. That's fact. So back to we had example that had eigenvalue 0. Oh yeah, here. Okay, what is the eigen? What is the? Is this invertible? Using the fact we just learned. I'm going one step forward. Sorry, I should teach this first. Okay, yeah, I should teach this first. Sorry, guys. So this looks familiar. Just get it for the first example, right? Determinant of A minus lambda I is equal to 0 is the way you can find eigenvalue, right? So this meaning this is called characteristic equation. Okay? Make sense? It has special names. David, can you read this?
Theorem 3A shows how to determine whether a matrix in the form alpha minus lambda I is not invertible. The scalar equation determinant A minus lambda I equals 0 is called the characteristic equation of A, and the argument example 1 justifies the following fact. The scalar lambda is an eigenvalue of an n by n matrix A if and only if lambda satisfies their characteristic equation. Determinant of A minus lambda I equals 0.
Okay, thank you. So try this. Find the characteristic equation of this thing. Guys, what is it? You don't even need to calculate. Just tell me the answer. If you use these two facts, then you can just get it right away. I want you to just tell me how this happened. I mean, we don't even need to calculate.
75 equals.
So what is this? A minus lambda I given matrix. Yes?
Is it in parentheses 5 minus lambda squared?
Oh yes.
3 minus lambda, and then 1 minus lambda.
Why? Good.
Wait, why is the first one squared?
Because you
have
determine has been twice.
Oh, okay.
Great. So first of all, I want to write this. A minus lambda I. Because all I have to do is just lambda I is just having lambda on the main diagonal line, right? Minus lambda, minus lambda, minus lambda, like this. So I want to copy paste because I'm lazy. And I want to write A minus lambda I, okay? And that is minus lambda here, minus lambda here, minus lambda here, minus lambda here. And I ask, find the determinant of this matrix. What do you do? Yes, because if the given matrix is triangular, then just to find the determinant, you just multiply the entries on the main diagonal. Okay? So this. Then our last job is finding the eigenvalue. What is it? Eigenvalue. Yeah. Am I asking too much?
Oh,
So
so
135. 135. That's 135. Eigenvalue is 135, meaning I'm going to have 3 different eigenvalues. Okay? Make sense? Okay, So here, so this thing matters. What is this? What is this? Let's read this. Okay, Christian, can you read this?
In examples 1 and 3, determinant a minus lambda I is polynomial. It can be shown that if A is an n by n matrix, then determinant A minus lambda I is a polynomial of degree n called the characteristic polynomial of A.
Okay.
The eigenvalue 5 in example 3 is said to have multiplicity 2 because lambda minus 5 occurs 2 times as a factor of the characteristic polynomial. In general, the algebraic multiplicity of an eigenvalue is its multiplicity as the root of the characteristic equation.
Okay. So back to the pre-calculus. Just remember the multiplicity. I mean, depending on, just you're literally reading this. I got a solution for lambdas 1, 2, 5, and they have different multiplicity. For 5, we have 5 multiplicity 2, and 1 and 3 we got multiplicity 1. Okay? And this will be important to find eigenvectors. This will determine, this will affect, the multiplicity will affect the number of eigenvectors, space. Okay, so let's say we have characteristic polynomial like this. And I ask you to find eigenvalue and multiplicity.
We could factor out lambda 4
Sure.
and then do
And then
that would be like we could factor that equation into like
yes, like
And,
foiling, right? One more time. So it's gonna be like this. I'll skip this. I trust you all can do this because you're already past calculus 3, right? Yes. So this. Then what is the lambda? I mean, what is eigenvalue? What are the eigenvalues?
0, 6, -2.
And then we have multiplicity 1, 1, 4. Okay? So read 0 with multiplicity 4, 6 with multiplicity 1, and 2 with multiplicity 1. Skip this. Any questions so far? No, so important, so important, so important. I cannot emphasize enough.
So it's okay if 0 pops up as an eigenvalue so long as it's not the only eigenvalue.
Pardon me, can you say it again?
So 0 is one of the solutions to that setup.
Yes.
And I remember earlier it said something about there being an issue if lambda is 0 since it has to be non-trivial.
Yes, yes.
It's okay if it shows up as a possible eigenvalue, just not the only eigenvalue.
One second. So we got 0 as one of the eigenvalues, right? Okay, that means we have the given matrix is not invertible. That was I was trying to say. Okay, so what is, you guys remember the definition of row equivalence? Row equivalence. Let's say A and B, matrix A and B are row equivalent to each other. What does that mean?
That one can be row reduced into the other.
Yes. So let's say, that's right. Okay, so we have so far we have, if we have two matrices, and I want to explain the relationship between those two. So far we learned one thing, row equivalence. Now we try to learn another thing, similarity. Okay, the definition of this thing is so A, B are similar to each other if this thing is true. It looks so confusing, but real learning. And this will pop up so many times in machine learning. Very, very, very many times. And then the reason we do this is to reduce the computational cost. One second, guys. Let's just read it. First, good voice. Anyone who want to? Okay, let's
The next theorem illustrates one use of the characteristic polynomial, and it provides the foundation for several iterative methods that approximate eigenvalues. If A and B are n by n matrices, then A is similar to B if there is an invertible matrix P such that inverse of P, AP equals B, or equivalently, A equals PB inverse of P. Writing Q for inverse of P, we have inverse of Q, BQ equals A. So B is also similar to A, and we say simply that A and B are similar. Changing A into inverse P, AP is called a similarity transformation.
Thank you very much. Very energetic voice. Okay, so let's just read the fact and then I'll explain what this means. If n by n matrix A, B are similar, then they have the same characteristic polynomial, hence they have the same eigenvalue. And then this is so important. And this is the reason why we try to have we try to construct a single matrix and then perform the same calculation with lower cost. Here, one more effect. Let's look at this too. It looks like similar. It looks similar, but they're not similar matrix. Maybe true, false. And then similarity is not same as row equivalence. Okay? They're different definitions. I guess we learned this next show. One more time. Yeah. So I'm trying to teach you why it is useful to use similar matrix. Just follow it. And okay, let's say I have B matrix like this, and I want to multiply these here. Any idea? What's these here? Just wait. 5, 0, 0, 3. I want to multiply this 5, 0, 3. What's 5? What is the matrix if I multiply this?
5009.
25009? Is that what you mean?
Yeah.
That's right, 2 is here. Okay, so I want to multiply one more time. I want to get D cubed. What would that be? 5 cubed, 3 cubed. Okay, I see the pattern. If I multiply one more time, then it's going to be 5 power 4, 3 to the power 4. Right? So that means if I want to calculate B, let's say power 10, that should be what? That should be what? 10 for the power. So it's like this. Okay. So let's say you start with some special matrix. There are only entries, the non-zero entries are only on the main diagonal. Then if you multiply that matrix many times, then it's gonna have the power like this. So let's say you multiply D for K times, then you're gonna have 5 to the K and 3 to the K. Okay, good. So let's say I have some other matrix, C, and then the C is like 2, 0, 7. What is it? C power to the power K. What is it? Yeah, 2K 0, 0, 7, 4, yeah, to the power K. Right? Yeah.
Can you notate that it's just the matrix with power on the outside of the matrix?
No, this is the
So
only one.
you have to write it for every
Yeah, yes,
variable?
yes. Because, yeah, that's totally. Yeah, so what you're saying is, say D is A, B, C, D, and then DK is not equal to A, K, B, K, C, K, B, K. Isn't it? Never true. Okay, so let's try this. Now we're trying to learn why it is useful to use similar matrix. This is one of the standard examples. I give you A, it's quite confusing. As David said, if I want to multiply this so many times, like K times, and it's gonna be a lot of work because I have to multiply each entries by each entry and add them for one entry. So for example, 7 to -4, 1. 7 to -4, 1. If I want to compute the first entry of this, okay, then I have to, how many times? 7, 7, 2, 4, plus the result of these two multiplications. So I need 3 operations for each entry. Right? So many times. So instead of doing this tedious work, I want to come up with some clever idea, which is about similar matrix, and somehow I want to utilize or take advantage of this structure. So let's say I want to multiply A squared. Okay, that is P D P inverse times again P D P inverse. Okay, so how I cancel this? P inverse minus P inverse times P. Yes. Then only thing left is D times D. Right? D squared. So it's going to be P times D squared P inverse. Okay, one more time. If I want to multiply A for 3 times, then it's going to be P D squared P inverse times P D P inverse. Do you see? Then again, cancel D cubed. Do you see, friend? Okay. So this is P D cubed P inverse. So therefore, I keep doing this. Let's say A to the power K. What is this? What's your right? That this is the main reason a lot of mathematicians or statisticians or data scientists use this. Let's say you have really gigantic matrix. Again, let's say you're like engineer from big tech. The data will be gigantic, so big, and you want to work. For some reason you want to multiply the data for many times, and it's gonna take a lot of time. So instead of just naively multiplying each entry by each entry like this, I want to use the structural similarity to reduce the computational cost. This is the way you do it. You're gonna use this so many times if you're using machine learning. Anyway, so this is the structure, guys. And okay, so now I want to ask, give me the formula for a to the power k using these two. Guys, try. Give me AK. What AK is each entry. How can you express each entry? Try it. You have to work it out. Anyone who want to solve this problem on the board? Inverse?
Yeah.
Inverse? Oh yeah, inverse. Inverse is the formula of inverse matrix is 1 over AD minus BC, and I think BA minus BC. Yeah, I'll just give you inverse of it. Inverse of P. So P inverse is 2, 1, negative 1. Yeah, there you go. Yeah, I'll try to be more kind. P inverse is this. Yes. Inverse is this. So whatever we cover until tomorrow will be the exam 2 topics. And then we'll review Monday, Tuesday, and then take exam notes Wednesday. And Thursday, further below. Yes. Oh, no. So you apply 2, 1 plus 1, and then you add those. That'll be the first entry.
That's
Anyone got an answer? Yes.
I got for the first row, first column, 2 times 5 to the k minus 3 to the k.
Mm-hmm.
And then second column, 5 to the k minus 3 to the k.
Mm-hmm.
And then second row, first column, negative 5 to the k times 2 plus 2 times 3 to the k. And then second column, negative 5 to the k plus 2 times 3 to the k.
Oh, you nailed it. Good job. This. You nailed it. Good job. Good job. Good job. This is given. P and P inverse, I'll give you if I ask it in the exam. I mean, then what? Do you know how to multiply those two? I mean, three matrices.
Should be part of the first two that multiply that product by the next one.
Okay, good. So, if your answer is different from this, yes.
Why would, or how would you find the values of P, D, and P? Like, if you have an initial matrix of A,
Oh,
there's no P, D, and P.
That's what we're gonna learn next time.
Oh.
Yeah, so that's another story. Yeah, finding P inverse is good. Oh yeah, not done yet. Last one. Okay, find the characteristic function, characteristic equation of this, and give me inverse, and give me eigenvalues, and that will be done for today. Find this thing and set this thing to determinant of A. Determinant of A, B, C is AB minus B. The answer should be. The answer is kind of messy. You have to use quadratic formula, but it's okay. Did you get real solution or not non-real solution? Since there's no time, I'll just okay, so this minus lambda, and then you get determinant using the characteristic equation, right? Which is what you should get, and then using the quadratic formula, you can. There's no real solution. Meaning, there is no real eigenvalue. So some matrix may not have eigenvalue. Be careful. Not every matrix has eigenvalue. If I go see tomorrow? Yeah. See tomorrow.
Are any kind of complex matrices?
Yes, but you're not going to deal with that unless you're in